Hi, my name is Youngsuk Lee, and I will be introducing you to what is required for an earthquake-resilient building. In 2017, an earthquake of magnitude 7.1 hit Mexico City, causing buildings to collapse and bury people alive. The goal of this video will be to find the conditions this turtle on a structure with minimum supports needs to keep in order to survive this devastating tragedy. Simulating the vibrations of an earthquake, you can see here that the bottom and top sections of the structure is reacting well to the motion with slight deformation. However, the middle section can be seen to deform, and you can even see a connection failing due to stress being focused to that area. This is due to poor connections between the ground columns and the middle column. And as there is nothing connecting the top section with the base or bottom section, you can see this type of motion has happened. Now, as you can see, with added weight, the structure fails catastrophically, killing the turtle. It is obvious here that we need some sort of connection between the middle top section and the base foundation. So after replacing the model, I added supporting strings connected to the base as shown. Now with the added supports, it is shown that the whole structure deals with the added weight better and deforms much more slowly. Not only this, but you can also see that the structure does not fail catastrophically, so the turtle survives. Now, as you might have noticed for an earthquake-resilient structure, the base foundation is crucial. Not only the base foundations, but the location of where the building is also decides the integrity of the base. If the structure is on a fault or a soil that goes through liquefaction, even with a strong structure, it will still fail. And for structures on a slope, the slope stability is decided by the factor of safety. When the factor of safety is less than 1, the slope will fail and the structure along with it. With this box of rice which is granular, I will simulate what happens to a slope made of granular soil under dynamic loading. Now, by using the data measured, I created this graph, which shows us that the original slope would have been deformed to 13.95 degrees in the 2017 earthquake. Now, we can assume here that if the slope has an angle less than that, it will be safe. But what is the maximum angle it can have for it to be safe? For this, we need factor of safety. Factor of safety for slopes under dynamic loading can be derived by using the formula shown in seismic slope stability in granular soils. Now, as a slope is stable when the factor of safety is greater or equal to 1, we solve this equality equation for beta, which can be rewritten for when n is equal to 0. So, in conclusion, Turtle needs to keep these rules to survive the 2017 Mexico City earthquake. First, make sure the building has strong supports, bracing, and base foundation, which are all strongly connected to each other. Second, be in a good location. No faults or soils that go through liquefaction. If on a slope, make sure the angle of the slope is less than 28.72 degrees.